In section 9.4, we're going to talk about vectors in 3 dimensions. And it turns out that all the math we did for vectors in 2 dimensions are going to work exactly the same for 3 dimensions. The only difference is you have z's instead of just x's and y's. So if you have 2 points on a vector, the initial point and the terminal point, you can still find the vector by doing terminal minus initial of each of the components, x, y, and z. So in problem 1, when I want to find the components of vector A with initial point 1, negative 4, 5, and the terminal point 3, 1, negative 1, to find the vector, all I'm going to do is 3 minus 1, 1 minus negative 4, negative 1 minus 5. So vector A must be 2, 5, negative 6. What if instead I tell you what the vector is, and I tell you the initial point, but I want to find the terminal point? Well, if you think about the terminal point as being x, y, z, and you know that you have to subtract terminal minus initial, and that's going to equal the x component of the vector, we can find out that x is going to be 0. Terminal minus initial for the y components has to equal 1, so y is equal to, nope, not 0, 2. And z minus negative 1 is going to equal 3, which is z plus 1, so z is going to equal 2. So the initial point is 0, 2, 2. And notice that the point is in, I'm sorry, not initial point, terminal point. But notice I wrote it in parentheses and not in the arrows, because the answer is not a vector. The magnitude of a vector, when we wanted to find the length of a vector, we squared all the components, added them, and took the square root. Well, we just have one more number to square and add before we square root if we're working in 3 dimensions. So if I want to find the magnitude of vector u in problem 2, I would do 3 squared plus 2 squared plus 5 squared and square root an answer. So the square root of 9 plus 4 plus 25, which is the square root of, 38. And I'd probably just leave that as the square root of 38. For vector v, 0 squared plus 3 squared plus negative 1 squared is going to be 9 plus 1, which is 10, so it's going to be the square root of 10. For vector w, 0 squared plus 0 squared plus negative 1 squared, it's going to be the square root of 1, which is 1. If we have 2 vectors in 3 dimensions, we can add and subtract them and perform scalar multiplication just like we did in 2 dimensions. So you just add the x components, add the y components, add the z components, or subtract those components. If you're multiplying a number by a vector, you distribute it to every component inside the vector. So let's say vector u is 1, negative 2, 4, and vector v is 6, negative 1, 1. When I add those two, I'm going to add the x's and I get 7. I add the y's, I get negative 3. And I add the z's and I get 5. So that's u plus v. If I subtract them, 1 minus 6 is negative 5. Negative 2 minus negative 1 is negative 2 plus 1. 4 minus 1 is 3. But for 5u minus 3v, I'm going to have to perform a little bit of work. So how about I figure out what 5u is first? 5u is 5, negative 10, 20. 3v is 18, negative 3, 3. Now I'm going to subtract them. So 5 minus 18 is negative 13. Negative 10 minus negative 3 is negative 7. And 20 minus 3 is 17. And that would be 5u minus 3v. If you have a vector, we had these things called unit vectors, where I was the unit vector along the x-axis, j was the unit vector along the y-axis, so now if I tack on a z-axis, I'm going to have k be the unit vector along the z-axis. And you can write a vector in either one of these forms. So in example 4, if I want to write vector u in terms of I, j, and k, I would write 5i minus 3j plus 6k. In part B, vector u is I plus 2j minus 3k, and vector v is 4i plus 7k. I want to find 2u plus 3v. Well, 2u is going to be 2i plus 4j minus 6k. And I'm going to add to that 3v, which is going to be 12i plus 21v. And, you know, think of the i's, j's, and k's like variables, like terms. So you're going to add the i's. You're going to add the j's. Well, 4 plus 0 is just 4. And you're going to add the k's, and 21 minus 6 is 15. And I wrote a v instead of a k there. And that is the end of part 1.